Okay, so what's the deal with implicit differentiation? So implicit differentiation is used to it's a technique used to differentiate what are called implicit functions. So what is an implicit function? Okay, well, so let's write some stuff down. Okay, so sometimes we want to describe a curve. So actually, let me start with that. So generally speaking, if I have some curve in the plane, this is not going to be expressible as a function of x. Y is a function of x, or x is a function of y, right? Let's say I just have some general curve like this. Maybe it crosses itself. Maybe it actually comes in two pieces. Sometimes that actually happens. So I want to consider points on this curve. Okay. Now, obviously, according to this, you can see very easily that this is not y is a function of x or x is a function of y, right? Why is this not, just to briefly recall, why is this not, say, y is a function of x? Why can I not describe y as a function of x in this case, Thomas?
It's not a function.
Yeah, how do you know that graphically? How do you know it visually?
The vertical line test.
Yeah, vertical line test. How do you also know that, say, x is not expressible as a function of y? The other way around. How do you know that? Fell's horizontal line test, right? Exactly. And we don't even have to have very complicated examples, although that is what I've drawn as kind of very typical. The curves we will deal with kind of do look kind of crazy like this, but we can also just talk about very simple curves like, say, a circle. Right? A circle also is not expressible as y is a function of x or x is a function of y. So we're going to say a few things about this. So first of all, how would you express these curves? How would you describe these curves to someone? And if you're not sure, think about this circle. How would you describe this circle to someone? That might be an easier way to think. Might be an easier question. How would you describe a circle to someone using, a function? You can say, okay, y equals x squared. That's a very easy example. How would you describe this circle to someone? If they say you wanted to graph this circle, what would you tell them?
X squared plus y squared equals 1.
Okay, good. X squared plus y squared equals 1, or 4, whatever the radius squared happens to be, right? So the idea is that these curves are just described by equations. That's really all I was looking for, right? They're just described by equations that involve both x and y, right? Perhaps this equation, I don't know what the equation on the left is. I kind of just drew a random curve, but maybe it would actually be given by something like, x cubed plus 2xy plus y to the fourth equals, 3. I mean, that's not what this curve is, but it could be something crazy like that. So maybe I'll put a question mark here just to kind of stress that. Okay, so that's the idea of implicit differentiation, right? This equation, x squared plus y squared, it does not define y as a function of x. It does not define x as a function of y, right? I mean, we can see that from the graph. However, it does define one variable in terms of the other, what's called locally. So let me write all this down, and then we'll talk about it. So sometimes x and y are related by an equation. And the thing about this equation is we cannot solve for one variable in terms of the other, right? Or else we would have, one as a function of the other. However, let's say these equations define local implicit functions. So the fact that makes these functions implicit is that they are not given to you by an explicit formula. They're given to you by an equation that they have to satisfy. That's what the word implicit means. Explicit would be if I just told you y equals x squared. That's an explicit function. So the implicit is kind of we already talked about with this equations. But what is a local function? What does it mean for this function to be local? Let's copy this circle. Okay. So what makes these equations define local implicit functions? Notice I actually also said functions, plural. Right? Again, because they don't describe one function. If they did, then we could just solve the equation for that function. Okay. So what happens? So even though this does not describe y as a function of x, for instance, let's say I was looking at this point over here, this marked point. If I only concentrate on the graph near this point, right, just near the point, not the whole graph, but just the graph near that point, is it possible to think of y as a function of x or x as a function of y? And the answer is yes, right? If I just concentrate on just that little area, right? Like pretend the rest of the curve does not exist, right? Pretend that all of this doesn't exist, and you're just concentrating on this little piece, this little arc of the circle. Is that one arc of the circle expressible as y as a function of x? Yes. Right. Now, what I've drawn technically is not x as a function of y because I've actually gone over that north ball, so it actually does not pass the horizontal line test. But it is y as a function of x. And in fact, how big can I make this arc before it fails to be a function? I can actually choose this arc to be kind of the whole upper half of the function of the circle, right? That, if I only concentrate on small pieces of the graph, I actually can get a function. In this case, obviously, we get y equals square root 1 minus x squared. And I can do the same with the bottom half, right? If I was considering a point on the bottom half of the circle, I can also consider y as a function of x here, right? I could say, okay, that's y equals negative square root 1 minus x squared. I can even do more than that. Well, I can also consider, say, the left part of the circle, right? If I didn't want to consider the bottom half, I could consider the left half. I can say, oh, this is x equals negative square root 1 minus y squared. But the idea is that this one equation, x squared plus y squared equals 1, can actually stand for many functions at once, depending on which part of the curve you're interested in. Now, if you had a very, very crazy example, like this, right? Again, this crazy example is not expressible y as a function of x or x as a function of y. Actually, I don't think I had to make it smaller. But many little pieces are, right? For instance, if I only look at this highlighted piece, or if I look at this highlighted piece, or let's say, so those are all y as a function of x. If x is a function of y, I could look at these green pieces. Right. So the pink pieces are y as a function of x, and the green pieces are x as a function of y. Right, the pink pieces satisfy the horizontal line test, and the green pieces satisfy, the pink pieces satisfy the vertical line test, and the green pieces satisfy the horizontal line test. Okay, now, I want to be able to do calculus on this. So that's what we're going to now talk about. So even though we cannot solve for these functions, we can still do calculus. Right, the circle, I do want to emphasize, the circle is an exception. The circle, I'm able to actually solve for these local functions pretty easily. But for a general curve, like if I just write down, say, xy plus sine of e to the x times ln of y equals 4, now that might be some weird kind of curve in the plane. I cannot solve for x as a function of y, even locally. Like I can't even do a trick like this with the square root where you get like two pieces or something, right? I mean, you have no hope For most curves I give you, you have no hope of ever solving for any piece of that function. But I still want to do calculus nevertheless. So even though we have no hope of finding an explicit formula for these functions, right, there again, very few exceptions like the circle. We can still do calculus. So let's jump into an example and see how that